Just a few seconds. So we were on the fourth question. This is W19 question paper 2-3, and we were on the fourth question. This one, and I think we are done most of it. We're going to start with a new paper as well. Uh, नहीं ये वाला paper we were almost done with this.
सी का थर्ड पार्ट कर रहे थे
इसका ठीक है, just 1 second.
वो कर रहे थे, उसके आगे से करेंगे.
अच्छा ठीक है. So this one, we were on this part. Okay, what's a chiral center? So it's when a carbon atom. Okay, this is start. It's a carbon atom, where the carbon atom is bonded to 4 different groups. So it's bonded to 4 different groups. Now this was done. And then you had draw the optical isomers using the conventional three-dimensional representation. You had to draw the chiral representation of a molecule, which we had figured out earlier. वो भी हो जाएगा. I think Isaac, we should start with a different one क्योंकि बाकियों ने ये नहीं किया हुआ था. So let's start with a different. Let's start with. Okay, so I'm going to open another one, and this time let's open an MCQ paper. So let's start with this question, and I'm going to start from the bottom. I'm going to do it the other way around because usually miss the organic questions. So let's start the other way around, okay? From the back. But let's start with the question number 20. We'll do organic questions first, and then we're going to do the rest of the questions. Now, starting with this question, reacts with, he's saying which substance reacts with trichloroethylene to give a chiral product. So the first thing is what is trichloroethylene? Okay, that's an ethene molecule with trichloro. That means 3 Cls. So there's 1 Cl, another Cl, and another Cl. There's 3 of them. So there's going to be 1 each. So at the end of the day, you need a chiral product, and the answer is going to be A. The answer is going to be A. Why? Because if you add a bromine molecule, a bromine is going to get added over here, and a bromine molecule is going to get added over here, and the double bond in the middle is going to go away. It would turn into a single bond, and you're going to notice that this carbon atom, the one that I'm highlighting, that's now chiral. It has 4 different groups. One side there is H, one side there is Br, Cl, and the other side there is this thing. So that is going to be chiral. So hence the answer is A. With HCl, you're not going to get chiral because if I add an HCl molecule, no matter where I add the H and wherever I add the Cl, it's not going to form a chiral molecule because the carbon is going to have 2 H's and this carbon will have 3 Cls. So it's not going to have 4 different groups. So it's not going to be chiral. NaCN and NaOH, they don't react with alkenes in the first place. NaOH probably will because it's a halogenoalkane as well. So it might substitute a Cl, but even then it's not going to turn chiral. As the next one is alkanes are saturated hydrocarbons. What type of reaction are alkanes most likely to undergo? So alkanes usually just undergo one type of reaction. कौन सा reaction होता है? What is the reaction that alkanes undergo?
Free radical substitution.
Okay, so it's going to be C. Then you have an alkene reacts with hot concentrated acidified KMnO4. So it's strong oxidation that's happening. So you're having strong oxidation, and they produce a single organic product. Uh, so there is this alkene. Now this is a difficult question. This is this alkene. What I'm going to do is I'm going to copy these, all of them. I'm going to show the working on the board. 1 second. And we're going to try and oxidize each one of them. Okay, so let me. So these are my 4 molecules. Now, when alkenes undergo strong oxidation, there are 3 scenarios. The double bond would always break, and it would always break, and it would turn into, if the carbon that was forming the double bond had 2 hydrogens, that would change into a carbon dioxide and a water molecule. Okay, then you have another scenario where the double bond is bonded to the carbon that was forming the double bond is bonded on one side with a carbon chain that would turn into a carboxylic acid. So it would turn into C double bond O. I mean, that particular carbon would turn into a carboxylic acid. And the third scenario is that if you have a double bond and on both sides you have a carbon chain, so that one would turn into a ketone. I mean, that particular carbon would turn into a ketone. So you have 3 scenarios. So we're going to do the oxidation of all these 3 products. Let's look at the first one. The first one is carbons connected to each other, and there's this thing, and there's this branch over here, and here's a double bond. So what's going to happen? The double bond is going to break. Okay, so remember that we're going to break the double bond. That's going to break in the middle. So I'm going to rub that off. Okay, so the double bond is gone. Okay, for some reason this is not rubbing off. I'm just going to do the working on that. I said the double bond breaks. So you have this carbon and you have this carbon. So what will this carbon turn into? It has a carbon chain on just one side. So if the double bonded carbon has a carbon chain on one side, that's going to turn into a carboxylic acid. So it would turn into double bond O and OH, a carboxylic acid. And what would this carbon atom change into? It has carbon chains on both sides, so that would turn into a ketone. The same thing happens over here. Strong oxidation, the double bond would break. This side has one carbon chain attached to it, so it would change into a carboxylic acid. And this other side would turn into a ketone because it has carbon chains on both sides. Then this one, again, the double bond would break. And this would turn into a carboxylic acid because there's only one carbon chain attached to it. And this side would turn into a ketone. And same thing happens over here. One side carbon chain, so that's a carboxylic acid. And this carbon atom would change into a ketone. So I've oxidized all the substances, and I need to figure out, okay, which one is giving me this product. I mean, that's the whole question. So I'm going to copy this molecule over here. I'm going to match this molecule with the ones that I've drawn. Okay, so let's. So here's my molecule. So which one? Now always remember the double bond is gone in the middle. Okay, so the double bond is completely gone. I mean, there's nothing there. Okay, that has been. I mean, the molecule has split at this point. Okay, that's gone. So which one is this molecule? Now, if you look at this molecule has a total of 1, 2, 3, 4, 5, and 6 carbon atoms in a line. So I'm going to count each one of them. So that's 1, 2, 3, 4, 5, 6, and 7 carbon atoms. So that's not possible. This is 6 carbon atoms in a line. That's 1, 2, 3, 4, 5, 6. There's a branch on the third one. Uh, but in a straight line, that's 6 carbon atoms. So this is the first one, that's not possible. I said, what about the second one? That's 1 carbon atom, 2, 3, 4, 5, 6, and 7 in a straight line. Again, that's not going to be the one. So what about this one? This one has 1, 2, 3, 4, 5, and 6 carbon atoms in a straight line. So that's a possibility. This one also has 6 carbon atoms in a straight line. That's 1, 2, 3, 4, 5, and 6. So this part matches for both of them. Both of them are candidates for your answer. So that's 6 carbon atoms in a line. What else do I need to match? That at one end there's a carbon, a CH3, and then a serial bond O. That's true for both of them. They have a carbon, a double bond O, a carbon, and a double bond O. So that's that. This part is there in both of them. The other end has a carboxylic acid, and that is also true. There's a carboxylic acid over here, and there's a carboxylic acid over here as well. Uh, the only thing that now matters is the position of this side chain. Okay, this is the only part that matters now. Where is the side chain? So it's the next carbon atom from the double bond O, which is why it's going to be this one. It's right next to the double bond O. Right next to the double bond O, it's going to have this carbon chain. ठीक है, is this clear? Abar, is this clear? Isa, is this clear?
Yes.
Yes.
ठीक है, so coming back to the original question, right next to the double bond. So coming back to the next one. The next question is question number 23, which is about a halogenoalkane, and he's saying a tertiary bromoalkane indicates that. So this is a tertiary bromoalkane, and it reacts with aqueous NaOH, and the mechanism of the reaction is shown. So remember, for halogenoalkanes, you have two types of mechanisms. For a tertiary halogenoalkane, this one, the mechanism is, let's make a tertiary halogenoalkane, this one, that you have a Br, and in the first step, the Br breaks away on its own. Okay, that's the first step. It's a two-step reaction. The Br is going to break away, and when it breaks away, it's going to form a carbocation. It's going to form CH3C, CH3, and you should also know why a carbocation is going to be formed. The reason a carbocation is going to be formed is because this carbon is surrounded by carbon chains. It's surrounded by carbon chains, and the alkyl chains have an electron donating effect, which is why the carbon over here does not have a very strong positive charge. The positive charge density over here on the carbocation is very, very less, and because of the alkyl chains, because of the electron donating effect of the alkyl chains, which is why it's the Br minus one. It's easy for the Br minus one to break away, because the positive charge over here is not going to attract it. And if the OH ion concentration is sufficiently high enough, so the stable carbocation is going to bond with the OH ion concentration, but it depends if it's really high. The other mechanism was for a primary halogenoalkane. Now, in a primary halogenoalkane, it's very hard for the Br to break away. Reason being that the carbon is not surrounded by a lot of alkyl chains. So the positive charge on the carbon is pretty strong, which is why it keeps the Br minus one attached to it. And you need the nucleophile to come in. It's going to come in and it's going to push the Br minus one away. Otherwise, the Br minus one is not going away. So in that case, it's a one-step mechanism. The OH minus one comes in and the Br gets knocked away. And in the middle, there's a transition state, which is that you have an H and you have a CH3. The OH is bonding to it and the Br is being pushed away and it's leaving. Okay, so it's not going to leave on its own. So which point in the diagram is correctly identified? So he's basically talking about the first step, the SN2. This is the SN1 mechanism, and this one is the SN2 mechanism for the primary halogenoalkane. So we're talking about the SN1 mechanism, and we have to identify which point in the diagram is correctly identified. So Y is the carbocation. So it's going to be C. It's a two-step reaction. A carbocation is going to be formed. So that's Y. Okay, that's your carbocation that's being formed. And then the OH minus one attaches to it. So that's your final product. So hence the answer is going to be C. This is not going to happen. This was for a primary halogenoalkane, and this is never formed in any case. So the C is the correct answer. Rida, is this clear? Abba, is this clear? Isaac,
Yes.
clear?
Yes.
So next one is bromoethane and chloroethane are added separately to water. Hydrolysis reaction happens. Which compound hydrolyzes more rapidly and what is the mechanism? So both of them, so what's the mechanism? They're not asking for SN1 or SN2. Basically, halogenoalkanes, they undergo nucleophilic substitution. What we discussed just now. They always have nucleophilic substitution that's happening. Achha, who's going to answer? Okay, which one is going to react first? Bromoethane or chloroethane? Which is more reactive? Which halogenoalkanes are more reactive? Like whose bonds?
Bromoethane.
Okay, that's more reactive. B is the right answer because the CBr bond is weak. Bigger atoms, they have weak bonds. And if they have weak bonds, then they can break very easily, which is why the hydrolysis would happen very fast. So remember, down group 17, iodoalkanes are going to be having the fastest reactions, and fluoroalkanes are going to be having the slowest reactions because the carbon and fluorine bonds are very, very strong. They don't break easily. So next one is an alcohol is oxidized to form compound Y and the composition is given and the MR is given. What could be the structure of the alcohol X? As a first thing, it is getting oxidized. Okay, that's one hint. Quickly tell me what the empirical formula is. It's what is 54.54 divided by 12? 36.36 divided by 16? 9.1 divided by 1. What are the values that you get?
4.545.
TK 4.55. This is
545.
okay, 5.45.
4.545.
ठीक है चलो next वाला option.
2.27.
2.27.
27.
ठीक है, this is 1. This is 1, right? So you're getting 4.55, 2.27 है और भी कुछ है.
So
Sir,
again,
the last one is 9.1.
You want to say 36? See, how do you convert this into a whole number? It's 1 second. Let me just quickly check. 36.36 divided by 16. Okay, that is 2.2725.
Sir, the last one is 9.1.
अच्छा हाँ ठीक है सॉरी ये मैंने गलत किया why did I write 1 इसलिए confusion थी. It was 9.1, right? इसको भी exact कर लेते हैं. It's 4.545, right? So ठीक है, that makes sense. वो I made a silly mistake. अच्छा अब let me so now tell me divide by the smallest. If you divide by the smallest, what is the ratio that you're getting?
It will be 2:1:4.
So it's going to be 2,
1 and 4.
1, and 4. So it's going to be C2. O is 1 and H is 4. Okay, that makes sense. C2, O1 and H4. And the MR is given. First, tell me what is the formula mass of the empirical formula? That's 2 carbons. That's 12, 24, 24 plus 16. That's 40. And this is 44. And the MR that they're talking about, the MR is given as 88. So that means that the actual formula has twice the number of atoms. It has the same ratio, but it has twice the number of atoms. So it's C4, H8, and there are 2 oxygens, right? That's the actual formula. And he's saying that's now this is compound Y. Remember, this is compound Y. Now this is not the alcohol. Okay? One thing is the alcohol X is getting oxidized to form compound Y. This is compound Y. Now starting, and you have to identify the alcohol. Okay? You don't actually have to identify this thing. You have to identify the alcohol. Now the thing is, if you remember primary alcohols, what do they get oxidized to? They get oxidized to aldehydes, which then further get oxidized to carboxylic acids. If you have a secondary alcohol, then they get oxidized to a ketone. So that is what is happening. Now the thing is that the molecule is going to have 2 oxygens. So one by one, try and figure out A, B, C, and D, try and oxidize them and see which one is going to give you 2 oxygens. So if you look at this molecule, is this a primary alcohol or a secondary alcohol?
Secondary.
Okay, this one is a secondary alcohol because the OH is right in the middle of the chain, and it's going to get oxidized to a ketone. A ketone is going to have 1 oxygen, so that is not the answer because your Y, okay, the Y that you have to form, it has 2 oxygens. Now this one is a primary alcohol. This one is a primary alcohol. This is again not possible. It's a secondary alcohol. So you have 2 options. It's either B or C. And I think you can get rid of B because it has 5 carbon atoms, because your Y has 4 carbon atoms. So it's going to be C. 4 carbon atom alcohol would turn into a 4 carbon atom carboxylic acid. Hence the answer is C. Is this clear?
Yes.
So next is the next one. You have this molecule. What is the product of the reaction between compound Z and an excess of NaBH4? This one is a reducing agent. So it's a reducing agent, and it does the opposite. Carboxylic acids. It's not going to react with carboxylic acids though. It would reduce an aldehyde back to a primary alcohol. It would reduce a ketone back to a secondary alcohol. So basically, you have an aldehyde and you have a ketone. They're just going to turn into OH. So simply turn them into OH. So that's it. So it's probably going to be A. Nothing would happen to the alkene. The double bond over here, that would turn into an OH, and the double bond over here would turn into an OH. You don't have to worry about primary alcohols and secondary alcohols. Just turn them into OH. They would always form the right type of alcohol. This is a primary alcohol. This one is a secondary alcohol. But you don't have to really care about them. Just turn the double bond O's, the carbonyl groups, back into OH groups. So A is the answer. Next is compound Q shows the following reactions. It's reacting with 2,4-D in pH. That's a test for carbonyl groups, C double bond O, aldehydes or ketones. So it's an aldehyde or a ketone. So we can get rid of propan-2-ol, not an alcohol. It gives a red-brown precipitate with Felling's reagent. Now remember this, going back to this, aldehydes can be oxidized to carboxylic acids. And to do that, how do you oxidize aldehydes to carboxylic acids? Uh, you need KNO4 or K2Cr2O7, or you need Felling or Tollens reagent. Okay? Felling gives a red precipitate, Tollens gives a silver mirror with this when this reaction happens. So it's either so Felling is going to give a positive test with aldehydes, but not with ketones. Ketones don't get oxidized. Ketones are resistant to oxidation. So this one is definitely, because it's giving a red brown precipitate, that means the molecule that we are talking about is an aldehyde, not a ketone. So that removes propanone from the equation. So now you're down to so now you're down to two molecules. Ethanol, which is this one, and propanol, which is this over here. So you're down to these two molecules. The final one is the iodoform test. It's a positive result with an iodoform test. Remember, iodoform reactions, they give positive tests with these. So they give a positive test with these two substances. Whether the molecule has this structure, CH3 acetyl bond O, a methyl group next to a acetyl bond O. Or the other one is you have a methyl group which is next to a C which has an OH, but which should also have an H, and the rest is R. So if either of these two structures are present, the iodoform test is positive, and that is present in ethanol. Because if you look at ethanol, like if you divide the molecule at this point, you're going to notice that this molecule uh, has the CH3 methyl with acetyl bond O. Hence, option A is going to be the correct option for this question. Okay, is this clear?
Yes.
So the next one is this tartaric acid. It's a big molecule, and you have it's found in many plants. A sample of tartaric acid reacts with excess of LiLH4 to form. So this is undergoing reduction. So that's a reducing agent. And remember, LiLH4 can reduce almost anything. It's a powerful reducing agent. So it's going to reduce a carboxylic acid back to an aldehyde back to a primary alcohol. It would also reduce a ketone back to a secondary alcohol. Remember this, NaBH4. NaBH4 doesn't work with carboxylic acid. It doesn't reduce carboxylic acids, but LiALH4 is going to do that. Uh, so all of them are going to get reduced back to alcohols. So coming back to the question, so product J is formed. So you have a carboxylic acid on both sides. They're going to get reduced. So I'm just going to draw this molecule. It's CHOH in the middle. I mean, that's the middle part. So there's CH and OH. The other middle part is again CH and OH. And this side is carboxylic acid. The carboxylic acid would turn into an alcohol. This side is also carboxylic acid. So after reduction, it would turn into an alcohol, a primary alcohol. So it would turn into CH2OH. This would also turn into CH2OH. This should be this is product J after reduction. Now, what happens when NaOH is added to separate samples of tartaric acid and J? So NaOH is a base. So what's going to happen? The base is going to react with the carboxylic acid. So the tartaric acid is going to react. Alcohols, they don't react. I mean, this is an alcohol, this is an alcohol, all of them are alcohols. So no reactions with NaOH. So only tartaric acid is going to react. So B is the answer. This is not going to react. You can remember alcohols are not really acidic. They only undergo one reaction. They're very, very weakly acidic. They're such bad acids that they ionize even lesser compared to water. So alcohols don't have any acid reactions, apart from the fact that they are capable of reacting with Na, sodium, and they're capable of forming salts with sodium, but very reactive group 1 metals, not with bases, not with carbonates. So hence B is the answer. I said then you have this thing. And he's saying that there's this molecule over here. And this molecule over here is bound with a little concentrated sulfuric acid, and a cyclic compound is formed. What is the skeletal formula of the cyclic compound? As a first thing, what is this molecule? This is a carboxylic acid, and it also has an alcohol. What happens when you have a carboxylic acid and an alcohol, and they react with concentrated sulfuric acid? Under the presence of concentrated sulfuric acid, esters are formed. So I'm going to draw this molecule, which is, there's a C double bond C in the middle. So there's an H and an H. And on one side there is CH2. And remember, you have to make a cyclic compound. So CH2OH. So what's on the other side? There's a CH. And then there's a carboxylic acid, C double bond O and OH. How are esters formed? Esters are going to be formed. You can remember, I've drawn this molecule over here. So esters are going to be formed. The H is going to be removed and the OH is going to be removed. So that they are going to be gone from the middle. And this is an ester link that's going to be formed. So you have a C double bond O that is attached to an oxygen. And you have to make the skeletal formula for this. So I'm going to come up with the skeletal formula. It's going to be, what would the skeletal formula look like? That's 1, 2, 3, 4, 5 carbon atoms. So that's 1, 2, 3, 4,
Hello?
and 5 carbon atoms. On the 5th carbon atom, there's a double bond O.
Hello, sir.
G.
आवाज आ रही है, sir?
Yes.
Acha. Sir, I was thinking, from where did this second carbon on the left after the double bond came from? मतलब वहाँ पे तो हमारे पास
I said, I made a mistake. There is no. I made a mistake. I added an extra carbon over here. This CH is not there. I mean, there is no CH. I mean, there's only one CH after the double bond. This is a mistake. This one is extra. So I'm going to remove that. I've just gotten rid of that. So they're basically just 1, 2, 3, and 4 carbon atoms. Brah. So there's 4 carbon atoms. Isko phir se hi kar lo. So that's 4 carbon atoms. That's 1, 2, 3, and 4. And after the 4th one, you have the double bond O. And then you have an oxygen over here. And there's a double bond at this point. So this is the molecule. Try and figure out which one is this molecule. It's probably not this one. You get next to the C double bond O. Next to the C double bond O, there should be. It's probably going to be C, I think. C looks to be the correct answer because there's this C double bond O, and on the next carbon atom there's a double bond, and on the neighboring one there's an oxygen. So there's an oxygen on the neighboring one, and on the next one there's a double bond, and then there's one more carbon which is over here. So it's C. TK, is this clear?
yes.
I said next one. Now we have infrared spectroscopy. So and he's saying what is compound P? TK just said compound P. What could be compound P? Now the first thing is, very quickly, TK, you don't really get a lot of information from infrared spectroscopy. Let me see where the data booklet is. Just 1 second. So this is the data booklet, TK. Always look for a couple of bonds when you're looking at infrared spectroscopy. TK, always try and look. Where is the So the first thing, this is infrared spectroscopy. Whenever you're looking at infrared spectroscopy, always go and try and find out this bond, the one that is over here, C double bond O. That's the one that's the easiest to identify. Okay, there's going to be a very strong peak absorption at 1600 to 1700. So if you have a look at your infrared spectroscopy, there is nothing at 1600. Okay? So one indication is there is no C double bond O. Now that would help you eliminate a lot of options. Uh, Propanol has C double bond O, that's gone. Propanoic acid has C double bond O, that's also gone. This is an ester. Esters also have C double bond O, they're gone. So the answer is D. Okay, is that clear?
Yes.
Yes.
Okay, so remember infrared spectroscopy. Always go and look for the bonds that are easiest to identify. Okay, which in this case was the C double bond O group, and there was no C double bond O group, which is why it was very easy. And the other bond that's very easy to identify is the OH group. The OH that has a pretty it has a broad absorption around the 3000 range. But the thing is that this absorption also overlaps with other absorptions like the carbon and hydrogen bonds. They also kind of absorb or vibrate at that frequency. So which is why you always, whenever you have an OH, there's going to be some absorption above 3000. So you can just for confirmation, although we know what the answer is, above 3000, this is your OH. This one around 3000, that's your CH. Okay, but they kind of get mixed up. And apart from that, very hard to actually distinguish absorptions over here. This is known as the fingerprint region. You can't really figure out a lot of things over here. As anyways, it was very easy to answer this question. Let's move to the next question, so the 31. I'm going to ignore this question. Let's move to 32. The first ionization of energy of chlorine is greater than that of sulfur. What factors contribute to this? So there's sulfur, and there's chlorine, and there's phosphorus. Why do ionization energies, why do they increase across the period?
Because the radius decreases.
But the group 1 to group 2, that increases. There's a dip at group 3, then 4 and 5 increases again, then there's a dip at 6, and then they start to increase again across the period. Acha, why is there a general increase?
Because the
Across.
radius decreases.
Proton number.
across.
ठीक है, एक तो ये कि one of them is that the protons increase, ठीक है, the radius, ठीक है, वो भी सही है, that's protons increase, so there's a stronger attraction. Radius very slightly decreases gradually. There's going to be a slight decrease, and the other factors, they kind of remain constant. So the shielding remains constant. They have the same number of shells. So chlorine has more protons. That's true. Chlorine has greater electron shielding. That's incorrect. Or again, if the second one is incorrect, the third one is also incorrect. Okay? You don't even have to look at the third one. That the covalent bonds in chlorine molecules are stronger. Since we are talking about ionization energies deals with gaseous chlorine atoms, not with bonded chlorine atoms. You can always remember this, that if the second is wrong, don't even look at the third one, save your time. The third one is also incorrect. So next is, well, and always remember this key. If the first one is incorrect, just mark option D. Don't even look at 2 and 3. If you're sure that the first is incorrect, it can't be A, B, or C, it's going to be D. And if the second one is incorrect, then it can't be, so if the first one is incorrect, the option is going to be C. If the second one is incorrect, the option is going to be, it's going to be D. You don't have to look at each option. Coming to question 33, you have liquid X and Y. They do not react with one another. They have identical boiling points. When So they have identical boiling points, which means they have kind of the same intermolecular forces. When a particular volume of X is shaken with a similar volume of Y, they form a liquid mixture Z. So, so they're not reacting. So I think they are soluble in each other. I said, so they are soluble in each other. Uh, the average intermolecular forces in liquid Z are stronger than the average of the forces in X and the forces in Y. So, so the mixture that is Z, the intermolecular forces are stronger. Which deductions from this information are correct? Mixing of X and Y is exothermic. That is true. Because the reason that's true is that here's what's happening. You had a mixture of X and X, and the intermolecular forces were weaker. There was a liquid which had Y and Y mixed together, and he's saying that the average intermolecular forces are weak. But when you mix them together, the X and the Y and they all mix up to form Z. Z is a mixture. They're not reacting with each other. So the intermolecular forces are strong over here. The intermolecular forces are weak over here, which means that when you mix them together, you're breaking weaker bonds. Uh, but when they get mixed together and they form these new intermolecular forces, the average intermolecular forces are stronger. So that's going to be more exothermic. So there's going to be a lot more energy released in bond formation, and a lot less energy would be required to break the bonds. So overall, mixing X and Y is going to be exothermic. Did you get this point? Rida, is this clear?
Yes, sir.
Abba? Okay, so it is exothermic. Now this one, the vapor pressure of liquid Z will be less than that of either liquid X and Y. That's also correct. What is vapor pressure? Uh, so what's vapor pressure? Vapor pressure is that if you have a container, a closed system, and you have these molecules of liquid, right? Any molecule of liquid. What would happen is that they're going to evaporate, and they're going to reach equilibrium. So vapor pressure is when the vapor, it's the pressure that is exerted by the vapor of the substance when it's in equilibrium with the liquid phase. And it can only be in equilibrium with the liquid phase if it's in a closed container, that it would be evaporating, but it would be condensing back again. So the vapor that would be formed, that would be exerting a pressure in the container. Now, if they're exerting a pressure in the container, when do you have more vapors? You have more vapors if the intermolecular forces are weak. If the intermolecular forces are weak, more gaseous vapors are going to be produced. And the vapor pressure that would be exerted, that's going to be larger as well. But since he's saying that liquid Z has stronger intermolecular forces, then the chances of vapors forming is going to be a lot lesser. So it's not going to evaporate easily. Liquid Z has stronger intermolecular forces. So there's going to be a lot less vapor produced, a lot less gaseous products produced in the container, and the vapor pressure is going to be a lot lesser compared to X and Y. Okay. Is this point clear as well? Okay. The last one is the boiling point of liquid Z will be lower than that of either. Now, liquid Z has higher intermolecular forces, so it's not going to be lower, it's going to be higher actually. So the third one is incorrect. So is this clear? And remember, you're not going to get a lot of questions on vapor pressure. There are very few questions on vapor pressure, but remember what is vapor pressure. I'm just going to briefly give you an overview of what vapor pressure is. Hopefully you've got an idea of what vapor pressure was. That in a closed system, when the vapor is in equilibrium with the liquid phase, the liquid is going to evaporate. It's going to produce a small amount of vapor, and that vapor is going to exert a pressure. Now, if the intermolecular forces are very strong, the amount of vapor that's going to be produced is going to be a lot lesser. And if the intermolecular forces are weak, then the amount of vapor that's going to be produced is going to be a lot more. Uh, and the vapor pressure is going to be higher. What else affects vapor pressure? Temperature affects vapor pressure. Like if you increase temperature, there's going to be a lot more vapor, and there's going to be a lot more vapor pressure. Okay, that's another thing that's going to affect vapor pressure. So just a little bit idea of what vapor pressure is. So let's continue with this question in the next class then, okay? We're going to stop here. Uh, just let me note this down. It's
Sir,
yes.
sir, can you tell me what are oxoanions?
Oxygen anions, SO42 minus, like SO42 minus.
Okay, sir.
But SO42 minus, that's. Nick, did you read them anywhere?
Yes, sir. It was a part of an MCQ. It was, although it was not the correct option, but it was the part
Okay.
of the question.
Okay, all these anions that are formed with oxygen, okay? NO3 minus 1 is an oxo anion, okay? So okay, let's continue. This is paper, concept paper. This is, just one second. This is 1913. Let me just note this down. And we're going to start at question 35 next time, okay? Okay, then take care. Allah Hafiz.